Hey guys, welcome to Lab 4. I'm going to be talking about the conservation of mechanical energy, and I'm going to go through the definitions portion. But last week's lab lecture was a little bit long, so this week I'm going to try to crop it down a little bit and just give you what you need instead of a more specific detail. So I'm just going to give you more of a general idea of what you need to understand for this lab. So first thing you're going to see in your lab is the lab is named Conservation of Mechanical Energy. So let's start off with what is energy, okay? So energy is anything that can do work, okay, or the ability to do work. So what is work? Okay, so if I'm telling you anything that can do work is energy, so we have a general intuitive idea of what work is, but we want to define that. So in physics, we define work as a force multiplied by a displacement. So this S just means displacement. Now, sometimes you'll see it written as force multiplied by D for distance. But you have to note that distance and displacement are related, but they're not the same. So let me give you an example. So if I have 2 points, and I wanted to walk from point 1 to point 2 in a straight path, the distance between these 2 points and the displacement of this path that I walked is the same. So in this case, S is equal to D. However, let's put 2 more points down that are the same distance away. But I told you, well, now you're on a path that looks something like this. Now, while the distance between the 2 points is the same, the displacement of the path that you took is different. So in this case, S does not equal D. So in this case, the displacement does not equal the distance. So it's good to think about in physics, in a straight line, the distance is the displacement, but in a curved line, the distance is not always the same as the displacement. That's neither here nor there, so let's talk a little bit more about energy. So, well, we know that this is equal to the work. I should write that for clarity. So work is force multiplied by a distance in a straight line, or displacement for a curve, or also for a straight line, because S is equal to D. So we need to note that anything that can push an object or apply a force to it and make it move has energy. Okay? So let's say that, let's draw a little guy here. Let's say he's pushing on a box. Okay? He pushes with a force on this box in this direction. And let's say sometime later you make a measurement and that box is now here and Joe is now here. He's pushed the box some distance or some displacement in this direction, and we defined energy as anything that can do work, or anything that has the potential to do work, or anything that can push an object and make it move. Therefore, it has energy. So in this case, we would say, well, Joe can do work on the box because he applied a force over some displacement. Therefore, these 3 dots just mean, therefore, Joe has energy. Okay, all this seems a little weird, but it's pretty easy to tell that living things like humans have energy because they can do work on objects, and applying a force over a distance we know means the object has energy. Okay, so it's clear that living things have energy, but in cases where things aren't living, can we still have energy? Well, I'm going to talk about that right now. So, for instance, if just write this up here. Let's say we have a ball and the ball is rolling. This just means that it has a rotation in this direction. Okay? And we have a pin over here, or a box, whatever you want to call it. So this ball has what we call a velocity, or speed, in this direction. Well, at time t, equal to 0, the ball is here. Now let's say sometime later, this rolling ball in this direction. Oh, my dog's about to bark. 1 second. Oh, so? No. No. Say the ball crashes into that box. I don't really need to draw it dotted here. The ball crashes into the box, and you can see the box is now leaning because the ball has crashed into it. So before the ball hits the block, it was moving, and therefore it had energy, right? Well, because it has the capacity to do work on this, it has energy. Okay? That's why. Now, if that's still confusing for you, we're going to go into detail about what is kinetic energy, what is potential energy. So kinetic energy is moving energy. Okay, so the moving ball before had the capacity to do work, and therefore it had energy. So kinetic energy. Kinetic energy, or moving energy. So the moving ball has the capacity to do work. Therefore, it has energy. Remember, anything that has the capacity to do work has energy. And well, this ball is moving. If I throw a ball at some object, you usually, let's say I was throwing it at you and I threw it 100 miles an hour, you would probably move out of the way, because if the ball hit you, it would hurt, because the ball has the potential or the capacity to do work, and therefore it would hurt really bad. Therefore, it has energy. Okay? So any moving object must have energy, and the faster the object moves, the more energy it should have, because it can do more work. So the faster objects move, the more energy. This all seems pretty intuitive, but sometimes students get mixed up on this a little bit. The more energy it should have. But why should it have that? Because faster objects, my pen is dying out here, faster objects can do more work. I'm going to keep repeating myself so that you guys really get the key points here. Let me switch my pen out. Hopefully this other one works a little bit better here. So the key point here is that the energy of an object due to its motion is called kinetic energy. Okay? This is the key point. Energy of an object due to its motion is called kinetic energy. Now, there is another form of energy. Okay, so we just talked about energy with motion, but what if energy, let's say, energy without motion? Well, can you have energy without motion? So let's think here. Let's imagine that we have a spring. This just is a spring, okay? And let's say that that spring has a length of L. And intuitively, imagine if I took my finger and I compressed this spring by 1/2 of its original length. So we're just going to squeeze the spring together, and then that leaves us with a spring that's more tightly compact, that has a length of L divided by 2, which just means that you have 1/2 the length of the original spring, and it's compressed over this distance. Well, if you take a spring and you compress it, which we've all probably done at some point in our life, well, that spring wants to, you could feel on your finger that it's pressing against your finger. So let's take this little spring that's compressed, 1/2 the length of the original, and let's put a little box in front of it. Well, this compressed spring can do work on this box, right? If we release our finger from the front of the box or the front of the spring, the spring is gonna spring outward, and it's gonna shoot this box across our piece of paper here. So the compressed spring can do work, right, on the box. And what does that mean? Well, it means it has energy. Right? This is the key point, that now we have energy without motion. Okay? Because this spring isn't dependent on it moving. We've compressed something, made it static, but when we release it, it shoots this. So you can have energy without motion. Similarly, for us boys that remember, now bear with me here, my drawings are not the best, but the same idea with the slingshot. Okay, imagine this being like a rubber band in between a stick. Okay, and then we have a ball inside here. Well, if you grab this and you extend you pull the rubber band back a distance twice as far as the original, well, this also has energy, right? Because we know if we release it, this rock is going to shoot. Because it has the, write this key word, it has the potential to do work on the rock, when it is released. So we can have energy without motion, and we can have energy with motion. Okay? So what does that mean then? So if I said these stars just mean they're key points you should think about. So what does this energy depend on? Well, in the case of the spring, the compressed spring with the box, the energy depends on how much you compress the spring. Right? So the farther and farther I compress this spring, the more and more energy that the spring has to knock this block away. Okay? If I just barely compress the spring just a little bit less than its original length, then it's barely going to move the box. But if I compress it to the maximum compression and then I release it, it's going to, with as much force that it can deliver to the box, it's going to shoot the box across the page. Okay, and then what about in this case? Well, what about the slingshot case? Here, and then G depends on how much we stretch the slingshot. So in this case, depending on how far we pull back this rubber band is going to depend on how far we can shoot this rock. Okay? So in both of these cases, what does the energy depend on? Well, it turns out that the energy depends on, in physics we say it depends on the configuration of the object. So in the previous case, flip back to it, where we had something that says energy of an object is due to its motion. It's called kinetic energy. Okay, well now we have something different here, where we're saying that the energy depends on the configuration of the object. So for energies associated with motion, you have kinetic energy, and energies without motion, we have something else. But what do we call that? Actually, before I tell you that, let's go into one more example, because you're going to be dealing with a similar idea for your lab. This is an energy without motion. let's say I have a ball, and I'm not going to try to draw a hand here, but the idea is that I'm holding this ball above the ground. So here's the ground. And I'm holding this ball up some height h above the ground. Okay? Now, what happens when I release this ball? So if I drop it, gravity, right? We all know that if we pick up an object and we drop it, that gravity does work on the ball, right? We see if we drop it, gravity does work by making it move. Well, what does that mean? That means gravity must have energy. Gosh. Sorry for my writing. Must have energy. Now, what happens if this is H, where the ball was before, and now I go up another H, so 2 times the height that the ball was before, and I drop the ball from here. So the question is, star, very important here, what does the energy of gravity depend on? How can I increase the energy of the gravity here? Well, increase the energy of gravity by raising the height that you drop the ball from. See, the force of gravity would be the same, right? Where the force of gravity is the same. Work is equal to a force times the displacement. So here the displacement is greater than here. So the force, we're saying, the force due to gravity is the same on both these objects, but the displacement is different. We're displacing this ball by twice the height, by twice as much as the original ball. So the force of gravity would be the same, but now it can displace more, and that means that the energy of the gravity has increased, okay, due to the height. So key point, energy depends on the height or the position. So let me flip it this way. It's backwards for the video, sorry, it gets a little confusing for me. So what does it mean to be waiting to become kinetic energy? We have a name for this in physics, and we call that the potential energy. So in the ball case, where we have a ball and we're dropping it and it's some height h, this is dependent on the position of the ball, right? Whereas in the case of the slingshot, this is 2 times the length. Or in the case of the spring, which is 1/2 the length, these depend on configuration, right? So we call these energies potential energy. And in this case specifically, this is the gravitational. This is the gravitational potential energy. And this is the elastic potential energy. Okay. So now we've defined kinetic energy and potential energy. So that's good enough for there. So let me just summarize what we've just learned on one single piece of paper, so that way you can refer back to the longer bits of the video if you need, but I'm going to summarize kinetic and potential energy here. So in summary, the summary of the idea is that anything that can do work is energy. That's the key point here. And we have 2 forms of that energy. We have, this is supposed to be T. This is I. Kinetic energy. Or motion energy is energy due to moving things. And the faster it moves, the more energy it therefore has. So in the case of the ball that we were throwing, the faster you throw the ball, the more energy it has. And then we have the potential energy. Well, we said that potential energy depends on its position or its configuration. And you can think about this as energy waiting to become kinetic energy. Okay, so this was the version of position, gravitational potential energy, and spring, or this was due to configuration. Okay? So that brings us to the lab finally, and turns out this video is just going to be long as well, unfortunately. Apologize, but there's also, I've written down here previously that there's other kinds of energy, okay? There's light energy, heat energy, sound energy, electric energy, chemical energy, and even this thing called dark energy that we don't know if it exists right now or not, but there's some good theories that suggest that it does. Light energy is interesting because it turns out that if you shine a laser at some object in space, it has the potential to move that object when there's no frictional forces. So it turns out that if you have a really powerful laser, you can actually move objects with it. Just keep this in mind, that what we're talking about isn't in totality that there are these other types of energies, but all these energies actually still come back to kinetic and potential energies. So the general equations, and I've previously written these down. So potential energy depends on position. Okay, so in your lab, you have something called gravitational potential energy. Well, potential energy is the mass. Well, in this case, it's the mass of the cart going down the inclined plane. The acceleration due to gravity, which is g, multiplied by the height, which is the height of the ramp. That's potential energy equation. The kinetic energy equation is, well, kinetic energy is the capacity of moving things to do work. Kinetic energy is the mass times the velocity squared, it's a squared term, divided by 2, or 1/2 mv squared. You might see it written. Okay, so this is kinetic energy. Mass of the cart times how fast the cart's moving at that position, squared term by 1/2. And then, well, what is mechanical energy? Mechanical energy is just the sum of the kinetic and the potential energies. So mechanical energy is the kinetic energy plus the potential energy, which is equal to 1/2 mv squared, which is the term for kinetic energy, plus mgh, which is the term for potential energy. And this is all given at the beginning definitions of your lab. This is just making sure that I include it in the lecture itself. And then for the lab, it tells you that the velocity is equal to the length, which is the length of the flag, which is defined when you read your lab, divided by the average time, which comes from the final time minus the initial time. You'll remember that all this means is that your initial time is when you release the car, and the car is released at t equals to 0. So 0 is the initial time, and then the final time is how long it took for the car to get from the initial position through the first photo gate. And this will be sort of the lab setup, where you'll have an inclined plane and you'll have a cart. What you'll need to know is that when the cart is at the very top of the plane, that's the kinetic energy, which, remember, we define kinetic energy to be, if I can find the piece of paper, we define kinetic energy to be 1/2 mv squared. Well, kinetic energy depends on a velocity, which we said, or the capacity of moving things to do work. Okay, so here kinetic energy is equal to 0. Well, that's because the velocity at the top of the ramp is equal to 0. So if you put 0 in here for v, you're going to end up with 1/2 m, which is the mass of the cart, times some velocity, which is 0 squared. So that's just, the whole term's just equal to 0. Okay, so the kinetic energy at the top is 0, but the potential energy is equal to something, right? It's all of your energy is stored energy at the top, which is potential energy. So all of the stored energy is at the top. There's no kinetic energy because it's not moving. Well, at the bottom, after some time, when the cart, right before it gets to the bottom and stops its position because it's blocked by a block or something, at this position, right before it stops, well, it's all kinetic energy. So your mechanical energy at the very bottom is equal to your kinetic energy. Well, why? Because at the very bottom of the ramp, the potential energy, which, again, we talked about, potential energy is mass times acceleration due to gravity times some height. But at the bottom, the height is equal to 0. So if you put 0 in for height here, well, your potential energy is just equal to 0. So at the bottom, your mechanical energy is equal to your kinetic energy. At the top, your mechanical energy is equal to your potential energy. It's important to note. And so an equation that you can look at, which is given to you already, is that your mechanical energy is equal to your kinetic energy plus your potential energy. So this, remember, is important. It'll help you solve these problems that come up in the question portion of your lab. So as the cart rolls down, the mechanical energy is transformed from potential energy to kinetic energy. So as this cart rolls down, if your mechanical energy is something, your kinetic energy plus your potential energy plus your mechanical energy, or plus your, gosh darn it, your potential energy plus your kinetic energy should equal your mechanical energy. So as your potential energy decreases as you go down, your mechanical energy will increase by that exact same amount. So the amount of potential energy lost is equal to the amount of kinetic energy gained. So let's do an example. I'll leave it at this example. This should give you enough information about how to solve all the problems on your lab itself. So I've drawn a little diagram here representing what you're going to have for your lab. And I put in some arbitrary numbers. But the question is, show that the amount of potential energy lost is equal to the amount of kinetic energy gained. So we're going to say that the height that the ramp is set at is 0.4 meters. And we're going to label that as height 1 because we're going to have a second height at the bottom, which we're going to say is 0.05 meters. Okay? And then we're going to have a mass of the cart, which is 3.0 kilograms. Remember, these are not the numbers for your lab. These are arbitrary numbers that I've entered so that you can see me work a problem. And remember that the velocity at the top before you release it, so v1, which is the initial velocity, is equal to 0. And then velocity 2 at the bottom is equal, right before it stops, this is maximum velocity reaches 2.62 meters per second. So let's work a problem. Maybe I can leave this in the frame. Just need to see the knowns so we can do the calculation. And write the question here. So if I were to ask you to show that the amount of potential energy, the amount of potential energy lost is equal to the amount of kinetic energy gained if I said, show that the amount of potential energy loss is equal to the amount of energy gained, well, how would you do that? Okay, well, remember, here's our equation, in that we have a kinetic energy and a potential energy, which is equal to the mechanical energy. So show that the amount of potential energy lost is equal to the amount of kinetic energy gained. All we need to do is enter our values for our mass, which is the same, which we've said is 3 kilograms, our velocity. Okay, so in this case we have a change in velocity from velocity 1 to velocity 2, and we have a change in height from height 2 to height 1, from height 1 to height 2. So to do our calculation, we're going to need m, which is the same. Let's go ahead and just divide that by 2. Our velocity, our final velocity is, let's just write this out so you can see velocity final minus velocity initial. And this is going to be plus m. Well, g stays the same because that's the acceleration due to gravity. And the height, which is h2 minus h1. So that's going to be, well, we're going to do h1 minus h2, okay, it's 0.4 to 0.05. So we would do h1 minus h2, okay? That's going to be our equation. So when we put it in, we're going to say that our potential energy, which is equal to mass times acceleration due to gravity times the height, is equal to the mass times the gravitational acceleration times h1 minus h2, which is equal to 3.0 kilograms. I'm going to leave the units out because I'm running out of space, times 9.8 meters per second squared, which is the acceleration due to gravity, times 0.4 meters for h1 minus 0.05, okay? And this is going to be equal to negative 10.3 joules. Well, joules is just the unit of measure that we use for energies. So whenever you solve equations in potential and kinetic energy, your result will be joules. And for our kinetic energy, we have 1/2 mass times the velocity squared. Well, this is a change in potential and a change in kinetic energy. So we're going to have 1/2 times the mass times velocity, velocity final minus velocity initial. Our final velocity is 2.62 meters per second, and our initial is 0, so you can just put your final velocity in because you're going to be subtracting by v1, which is 0. So you're going to have 1/2 times 3.0 for the mass, and 2.62 meters per second. Don't forget, we need to square this term. Don't make the mistake that I did. And it turns out that this is equal to 10.3 joules. Well, that means, thus, the potential energy change is equal to minus the kinetic energy change. So on your lab, you're going to be asked similar questions, maybe not exactly like this, but you'll be asked questions dealing with potential energy and kinetic energy, and that potential energy plus kinetic energy is equal to your mechanical energy. Okay? Use these same rules and guidelines, and Here we've proven that the amount of potential energy lost as the amount of potential energy lost as we go down the ramp is equal to the amount of kinetic energy that we've gained, because we can see here that we've lost 10.3 joules and we've gained 10.3 joules. So this shows our conservation of mechanical energy. Enjoy your lab. Sorry it was long, but I felt like it's sometimes more beneficial to make it a little bit longer than being too short. So, and just remember, when you make these submissions for your labs, please try to submit them in PDF form, and make sure that your pictures or your PDF is oriented in readable fashion and not some strange landscape orientation, because it makes it really difficult to grade your labs, constantly having to flip pictures. So, alrighty, that does it for Lab 4 lecture portion. Thank you very much. Have a good day.